Welcome everyone. Today we're going to talk a little bit about how LiveView is a process. My name is Jason Stiebs. You can find me on the website formerly known as Twitter at Peregrine. I have also some links to my other social media, Twitters that you can follow me at there. And I'm Peregrine on GitHub. So I'm on the Phoenix core team. I've been using Elixir for a long time. One of my favorite little contributions to the Phoenix project is the microsecond symbol in the logs. So when you see that, just think of me. I ran a contracting consulting firm for a decade, and we've been putting Elixir into production since before it was V1, maybe too soon in some people's eyes, but we've never regretted putting Elixir and Phoenix into production so far, and I don't see that changing. This year I joined Flat.io as a Phoenix framework specialist. My job is to make sure that Fly works really well for Elixir and Phoenix and to advocate for the Elixir and Phoenix community, along with Chris. So if there's something that is not working well for you in Elixir or Phoenix and you need someone to reach out to, feel free to hit me up in the social media platforms, DM me or whatever, do my best. So you might have heard my talk already or you might have read my blog post already about how LiveView is a process, which is good news because this talk also has quite a bit of overlap with Chris's keynote this morning, which wasn't on purpose. It wasn't planned. But I heard a probably made up statistic somewhere that when you're giving a talk or a lecture that you're lucky if 1 out of 3 people actually get the message. And his advice was to repeat it 3 times. So if you read the post and you saw Chris's talk and you see this talk, you should be in good shape. So the 3 things I want you all to come away with today is, what is a process? How does it work? How does it run on the Erlang virtual machine? How that works in the context of a LiveView. LiveView is a process, so how does a LiveView work as a process? And ultimately, I want you to come away with some confidence. A lot of people come to LiveView and they can be really productive right away. They can put together heeks, they can handle events, they can do some JavaScript. They can get a powerful website together really quickly. But they really don't know what's going on underneath, and it can feel like a black box. I've known people who've been working in Elixir for a year and put out a lot of websites, and they still kind of a black box, what's going on here? Why do I have to use tasks or now async assign to load stuff asynchronously? Why is that important? Why can't I just run a query in my mount? If we can come away from today with a better intuition of how a process works and how it runs on the Erlang virtual machine, that would be ideal. So we're not going to get super into the weeds with a lot of code. There will be some code and a demo. I'll just give you a little preview. So what are processes? I think the best way to kind of start is to say what is not a process, and a process is not a thread, and it is not an operating system process. I think people who come from other languages, they hear the word process and they think it's something expensive, something to be used only when you really need it, or something to be kind of maybe a dangerous thing to use. And that's probably because threads and operating system processes have quite a bit of overhead. And we do not have that in the Erlang virtual machine. So if you come from another language and Elixir is not your first language or whatever, erase those from your mind as best you can because it's not a good metaphor. What a process is the concurrency primitive for the Beamer. It is how you do concurrency in the Erlang virtual machine. I mean, really, if you think about it, is the fundamental the fundamental primitive of doing any code. If you type self in any context of running Elixir code in the Erlang virtual machine, you'll get back a process ID. So you really cannot execute any code unless it's running in a process some sort. This is how you start a process. This comes right from the Elixir guides on processes. You just type spawn, pass it a function or a function it can call, and it'll execute it. It'll immediately return a PID, which is a process ID. A process ID is globally identifiable, so no matter what node you're on, or if you have a process, you have a node running in Japan, a node running in Orlando, and a node running in Frankfurt. If you have a PID, you can send a message to it. It's no big deal. And a PID is so important in the Erlang virtual machine. If you look at the type spec on either Elixir or Erlang, it's a PID is right next to integers and floats and tuples and atoms. It's not like some secret integer or some secret tuple. It's a fundamental type. And when you think about when Erlang was made in the 80s, right, that's pretty radical, right? In the 80s, they only had single core CPUs and stuff. So a PID is fundamental. It's exactly it's part of the system. And when you run code in a process, when you call spawn, you're just running Elixir code, right? So everything inside of a process is completely immutable. You can't share values between two processes and have something you work with change from underneath you. You can't change something and have an effect somewhere else in the world. Suffice to say that every process is completely and totally isolated. When you execute in a process, you can be certain that what code you're reading, what code's being executed, is not going to change. And for me, that's like one of the best parts of working in a functional language in general is, it's what you see is what you get. You're not going to have a situation, like in JavaScript, which is pretty common, where you have a reference to some object and it's changed or it was deleted, but you're still working with it, and you get really hard to debug exceptions. It doesn't happen with Elixir. It doesn't happen in Erlang. And that's because of message passing, right? Like if you want to talk to a process, you have to send a message. And if a process wants to talk to the outside world, if you think back to that first example where it just added 1 plus 2, the only side effect that process had was making your CPU just a little bit warmer, right? It didn't output something, it didn't communicate to the outside world, it didn't log, it didn't send a message or receive a message. So if you want to send a message and you're in a process, or if you want to communicate to the outside world and you're in a process, or do I/O, or do basically anything in Erlang, you're going to end up sending a message whether you believe it or not. And in this example, I'm sending myself. The self function will always return the current PID of the current process, the tuple present LiveView as a process, which a little bit of foreshadowing because messages are processed in order. I'm kind of telling myself to do this presentation a second time after I do it, and I'm definitely not going to do that again. So I'm going to do it one time. But another thing to keep in mind is that tuple is fully copied. So when you send a message, whatever's in your message is going to be copied into that new process. This helps us have the guarantees that, one, we're not getting a reference, so we're not going to change the value or have the value change on us. And two, it allows for a lot of really cool stuff like the parallel garbage collector and other stuff. But yeah, so anything you send as a message is fully copied. And that also gives us transparency. Like that lets us send a message across the globe because we're copying it across the globe and we don't have to think about it, right? If we had to have a special like send distributed or something, that would make send way less useful, right? Because we can just call regular send and it has the same semantics whether you're sending it locally or globally, it's pretty cool, I think. And yeah, here's our little model of a process. You could think of this as sort of a gen server or a hand-rolled process. Kind of starts at that spawn, and in our very first example, it did 1 plus 2 and it was done, right? It went right down to exit. It didn't do anything else. In a typical gen server or a process that you want to live for more than a microsecond, you'll do a receive and you'll basically wait for a message, right? And messages come in your mailbox. They're first in, first out queue, so it's just like a list. And when you receive a message, it'll pattern match, it'll execute some code, and then maybe it'll update some state. That's optional, you don't have to have state in a process. And then it'll wait, and it'll just continue to do this forever. If you're familiar with functional programming, or if you're familiar with redo or React's use reducer or Elm, this is just a reducer, basically. We're reducing over the mailbox as a list. It's kind of a stream reduce because it just goes on forever as long as we keep receiving messages. It doesn't have an end unless we tell it to end, and it's building up a state. In the case of a LiveView, our state would be the socket. That's our state that we build up every single time. And our mailbox, a LiveView also has a mailbox, and that would be where events and stuff come from. And if you kind of think, zooming in on the computer a little bit, this is exactly how our CPU works, right? Our central processing unit. It receives code, it updates some state or some RAM, and then it might have some output on the outside world. In the example of a CPU and a process, it can only handle one instruction at a time. So each process is completely serial. It runs the code from top to bottom, and if you want to do something in parallel or concurrently, inside of a process, you can't, right? You have to spawn a new process that'll do stuff concurrently in serial. And this works just like how a traditional CPU works. And like how most programming languages work in general, right? It just runs from top to bottom, and then you have to use a different library or threads or an operating system primitive in order to do parallelism or concurrency. In a modern CPU, again, hand waving. This isn't exactly how they work, but if you have multiple cores, They all do stuff in parallel, but they still share the same RAM and the same memory. And this is, shared memory and shared CPU is kind of the big problem. If you think about Rust or you think about other programming languages that do parallelism and concurrency, like that's their whole thing that they're thinking about, right? Like the ownership system in Rust is entirely to make sure that the memory that you share between functions and you share between processes is not used after it's been freed, or it's not changed without having correct ownership of it. And other language, like Ruby has got like 4 different ways of doing concurrency and handling, you could do threads, you could do event machine, you could do fibers, and I think they even have an actor now, for example. In Node, you really only have one, and that's, do something asynchronously with promises. But everyone's trying to solve this problem, is how do we use our CPUs? How do we use these many cores that we have? And in Erlang, we just kind of punt on it, and we say everything runs in a process, that process runs in serial, and then let Erlang take care of the rest. Which for you as a developer is like kind of a big mental load, because you don't have to figure out, all right, is my library I'm using thread safe? Does the library use the same asynchronous primitive that I use? And there's not really a lot of languages that have good answers here. Like Go is the only modern languages that came with concurrency built in, right? Like even Rust, right? You have to pick a runtime that does your async, and you have to use libraries and stuff, and it's not exactly built in. They're adding promises and stuff, but it's, it's subtle, but it's, because it's built in, because it's part of the language, we can use it. And the reason we can use it is because of the scheduler. If you're familiar with operating systems and the schedulers in operating systems, the Erlang the Beam is basically an operating system. It has a scheduler that is given processes and given RAM. Or you give it a CPU and RAM, and then it will run your processes concurrently. And remember, Erlang comes from the 80s when they only had single-core CPUs. So it was really just built for single-core CPUs and running stuff concurrently on one CPU. So your scheduler will say, you've run long enough, I'm going to run this other process, or I'm going to run this other process. And it chooses which process to run with heuristics, and it tries to most efficiently use the CPU you have available. Today, it'll run, by default, it does 1 scheduler per CPU. So if you have 4, I think this one's got 8. So when I run an Erlang virtual machine, it pops up with 8 schedulers. You can configure it if you don't want to use all 8. You can just say use 4, 2, or 1, or whatever. And it kind of just magically handles everything for you. The scheduler is also kind of the reason that it's really, really hard to just rewrite the Beam in Rust, or put a Beam in the browser, right? There's a lot of work that went into making this work really well, and we all benefit from it. Just some random facts if you're into this kind of thing. A process, when you give a process to a scheduler, it only has to allocate 300 words of RAM, which is about 600 bytes. It can start and stop a process in microseconds, and you can create millions of a second. Like you've all seen the demo where someone creates a million processes and they do something and then they all shut down. Anyone's laptop can do that, a Raspberry Pi can do that. And that's just not possible using threads or operating system processes. It's really not possible in a lot of languages themselves. It can also magically migrate processes between cores, between schedulers. So if a scheduler is busy and you can steal a process from another scheduler, and I don't know exactly how they do that, but it's pretty cool. And before I said it always copies values, but it doesn't always have to copy values. It has heuristics where it can, if a binary is too big, if we have a very large string or JSON payload or something, it'll actually do reference counting and just pass a reference around, assuming you don't send that to another node. But you don't have to think about any of this, right? The scheduler just does it for you, right? And it also does parallel garbage collection. What I alluded to earlier is it's kind of a really cool thing that I think Go might have a parallel garbage collector, or maybe Java does now. But it's pretty special that you don't have, when other languages garbage collect, like Ruby or JavaScript or even Java, they usually have to pause the world. And they say, all right, what objects can we delete? And this creates a lot of lag in apps, like Ruby apps and Ruby servers. And it ends up, your memory ends up growing pretty quickly because the garbage collector cannot quickly enough, tear down all the stuff you allocated, all the garbage you've allocated. But Erlang can just do that while other processes are running, right? If a process is asleep, it's no big deal to garbage collect it because it's not running right now. You don't have to pause the world; you can just pause the one process, and that's pretty cool, right? So there's just some random facts and trivia about the scheduler, but you should really just know that the scheduler is magic, and it's incredible magic. All of the stuff that we do with Erlang and virtual machine would not be possible without it, and yeah. So LiveView, we talked a little bit about processes, like how does this fit in with LiveView? I just want to do a quick survey just for my edification. So how many people here have put LiveView in production, with users? Could be your cat, a user, I guess. All right, cool, keep your hands up. How many of you learned Elixir just in the last year or two? Just a couple, not too many. That's cool though. Thanks for coming. This talk is mostly for you. Yeah, so what is a LiveView, right? A LiveView is just a gen server. So this is the code right from phoenix.liveview.channel. You can look it up on the GitHub. It's like the first 4 lines. I think I deleted a couple like module constants or whatever, module attributes. But it's literally just, we create a gen server. It has a start link like every other gen server. And it's called the channel because a LiveView is built on top of Phoenix channels. So we don't have to reinvent the world every time. But I just wanted to prove to you, it's literally a process. Here it is. And here's that same kind of flow chart that we had before. If the words are too small, you can't read, I'm going to post this online later so you can look at it more closely if you want. But if you squint, you can very easily see the process model we had earlier. Like this, right? So go back. So at the very top, we have the dead view. That's just sort of like the initial load of loading in HTML and stuff. Skip over that, and you get to your mount, which is just spawning a process. Get your handle params, which is just a function you call right after spawning a process, a special event it gets called, and then render, which takes whatever assigns or state you have and renders it, and then it jumps right into a receive loop, and it's just waiting. And from there, it's all just regular process stuff. So it can handle event, which is just a special Erlang message. You can do handle info, handle call, handle cast, just like you can on a gen server. And then it's got handle continue, just like a gen server as well. We have a secret second process that the LiveView process monitors, which is the browser. In many ways, it's just another process that's running that you communicate over with message passing. Like when we send a diff down to the browser, we just send a message to the browser over WebSocket, and then the browser process figures out how to render it. And when the browser, when you browse away or you change the URL, it sends a patch message. In LiveView figures out how to handle it. When you push an event or click a button or something, it sends in a push event, which we'll see in the demo in a second here. But really, we have a LiveView monitoring a browser process. And then kind of crucially, if there's ever an error or an exit, either that comes from the browser or the LiveView, it reconnects. So we have a supervisor. This is kind of where we talk about supervision or supervisor trees. The process crashes, we restart the process, we reconnect. And that can come from the browser. A browser, JavaScript error, browser error can happen in the browser. That can cause LiveView to restart, and vice versa. This is just like the process model we were talking about earlier. Our state is the socket. Our mailbox are just the events that come in from the user. It's kind of important to remember is that every single user who comes gets one of these, right? So every single browser, every single person who visits our website that's a LiveView, they have state, they have a mailbox, and they're receiving events, and everything happens serially. So every handle event and the handle info, every patch event, whatever code you have in those handlers is going to run all the way to the end before it can handle any other message in the mailbox. So we'll do a quick demo here of that. Hopefully this goes well. I just wanted to show, so can everyone see that all right? Yep. So this is a pretty basic app. I can click this checkbox and it'll start, let me refresh the page, that number is way too big. I click this checkbox and it'll start a hook that just spams us once a second. It's just a set interval type thing. I can stop it and it'll stop spamming us. And then we have a boom event, which puts a boom event in the list here, and in 4 seconds, it starts loading up. It takes about 4 seconds to load. So let's look at the code for that just real quick. We got our boom event. It sends a message to ourself, which it does, and that gets puts on the mailbox, and then it immediately inserts an event and renders that. So we kind of saw that where we clicked boom and it immediately rendered it. Then the scheduler sees that we have another message in the mailbox, and it's a load event. So it goes down to handle info and it executes our handle info, and this sleeps for 4 seconds. You could think of this as a slow API call or something. And it takes all of the 4 seconds to put that there. But things start getting kind of bad. So here we have our spam events happening. They're happening once a second again. When I press boom, the spam events stop. And we have to wait for 4 seconds to see what happens next. I'll pause the spammer so we can look at it. But you can see here we had our boom. 4 seconds later, we had our loaded event. But during that, we got 4 other spam events that just kind of built up in the mailbox. And it wasn't able to handle, our server was not able to handle the spam events until it handled the 4-second pause, because the processes are run serially, and the scheduler's not going to let you run if you're executing stuff. It's not going to stop and let you do the next mailbox item just because one mailbox item is slow. It's going to do every single thing one after another. We never handle mailbox items in parallel. Another kind of side effect of this, so if we start the spammer again, and when we click boom, like nothing happens, right? Like the user can't click around, like all the events that happen on the page just won't happen. Everything just gets slow and kind of janky, like things are just popping in and out of existence. This is, suffice to say, like, when Chris was talking about async assign, like if you have something that's going to take seconds to load, use async assign going forward, or use a task, or use something. And if you come from JavaScript, think of this as the UI thread, right? This is our UI process. If we block that, then the user can't interact with the page. The user's going to have a bad time. So do your very best to not block a process. And this goes for kind of any process, right? Unless your process is going to be doing something for a long time and nothing else, you shouldn't block it, right? Like if your process is going to be handling millions of messages a second, you really, really shouldn't block it. You should be spawning a process to do some other work so that it can quickly catch up. If you look in the observer, you look in other debug tools, it'll call this reductions, right? When a process has a high reduction count, that means it's run through its send-receive loop a whole bunch, and it's if it has a large mailbox that just keeps growing and growing, that means you're doing something too slow, or you're overloading that single process. So that was demo number 1, and I have a second demo. In Erlang, there's this really cool module called DBG, and you can set up basically what DBG allows you to do is to trace just about everything. So in this case, we're setting up dbg.p, which stands for process, and we're telling it to trace the current process, and M is shorthand for send and receive. But this tool is extremely powerful. Like you can just monitor a module for any function call for that module. You can module a single function and monitor how long it takes. It's an extremely sharp tool, and I don't have enough time to go into it. And frankly, I don't understand it that well. The doc is really big. But what this will do is this will log every message that this process sends and receives to the terminal. So we can kind of already see that. So if we scroll up here, just want to make sure everyone can see that all right. Everyone read it back there? Good. Okay. Here's the first message. This is where we set up the trace. We got our log, and then we see here, this is actually how logging works. So we have a gencast, and we can see our log message right here in the trace. The little bang means that I sent a message, so my process sent a message to this. And then we have down here the initial load. So you can see the HTML. So one of the problems of the debug module is everything's in Erlang syntax. So this is a map, and these are strings. These are binary strings. So if we go down here and we click the boom event, and we look at the terminal, scroll down, got to scroll through all the Erlang noise. We'll see here we have the message that was sent from the browser. That was an elixir.phoenix.socket.message. Here's our payload event boom. And this was a message that was sent to our LiveView. Like that's what you can kind of see it here. And you can see the result here, right? So we sent a message to ourselves. That's what this little, live demo stuff. Let's scroll up. We sent a message to ourselves saying load. We received that message load. And yeah, we have the log message again, and then the diff. So like this is just exactly what's sent down the WebSocket. If you look at the WebSocket network panel in the browser, which I could show you, although I couldn't get this to look super good, but we'll try it out anyways because we have time. So let's zoom in. You can kind of see it down here. Zoom out. You can see each one of these events kind of replicated in the WebSocket, right? So this is kind of like debugging a WebSocket, but in the browser process, not the server process. But yeah, you can just see all that's happening here is down the socket, we're sending text, and we're sending this JSON payload. And if you scroll down, we should see the text boom. Yeah, here it is, boom. In this case, we're not sending a map, we're sending something called an IO list, and that's why it's all kind of weird looking. And that's just slightly more efficient for Erlang to send over the wire. So when you see these weird lists everywhere, it's just an IO list. But you can, again, here's another diff that popped up. You can see that's a diff payload. There's really nothing fancy happening here, right? Like all it's doing is looking at our state. It sees that our socket.assigns has changed, and it is rendering the diff and pushing it down the pipe. Like the diff is a little bit of black magic, but you really don't have to know how diffing works to use LiveView. But you should know that how a process works and how it's sending and receiving messages. So yeah, just a quick reminder, DBG module in Erlang. If you ever find yourself stuck and you really want to know what's going on, this is the place to go. And yeah, so this is I had to add this slide in because after Chris swapped his talk time. But async assign, that's coming down the pipeline, and that'll really help you make the jank from clicks and button presses go away in your live views. You should use it as much as you can. I think we should have probably added it to Phoenix like 6 years ago in hindsight. But you can't go back in time. We have it now. It's kind of, and if you're from JavaScript, it's kind of a promise. So if you ever want to play a joke on Chris, ask him about why he added promises to Elixir. But yeah. So yeah, in summation, LiveView is a Beam process. They're extremely cheap. Every single visitor gets one, and do your very best not to block it or bloat it up and make it too heavy, because you'll end up with kind of a bad user experience. Yeah, that's it. You can find me on Twitter at Peregrine.